So, welcome, sir.
Thank you for inviting me.
Can you explain a little bit more about this Semiconductor Mission 2.0?
First mission was all about establishing fab, the hardware. The second mission is all about IP creation.
What kind of education do you think the students should undergo?
You requires a broader education. You will talk to your friend that, hey, look what I've discovered, let's make a product out of it.
One word to describe your PhD guiding is
Give them freedom.
what is the future of education? It is degree or skill?
None of the two.
Welcome to IITH Postcard Series. I am your host, Professor Ashok Kumar Pandey, Dean Academics at IIT Hyderabad. Today we are having a man who has worked in the sensors, and his sensors not just being used in the ISRO mission starting from the Chandrayaan, but he has also established state-of-the-art facility where the sensors are fabricated and completely come out as a shape and being used in the industries. So, welcome, sir, to IITH Postcard Series, and thank you for accepting our invitation.
It's a pleasure, Ashok. Thank you for inviting me.
Thank you, sir. So today we are going to talk about the initiative that government is taking. I would say that I was fortunate when you started working in BAMS at the same time I joined. And today we see that India has progressed a lot in that direction, and with your device now after, I would say, mostly 20 years or so, coming into place and being used in our systems. So what is your view on the initiatives which are being taken in terms of ISM 2.0, and another one is the recent collaboration with the US? Your views, sir?
Well, these are initiatives which are really, really required for the country. It was required even earlier. Initiatives like this had started 15, 20 years ago. It just couldn't mature, maybe for the lack of funding or lack of will or whatever it is. But it's high time. It's critical time that we have, particularly for silicon and particularly for electronics ecosystem, with including chip production and all the assembly, testing, system building, all of that. It's very, very important that we get that done in India and we get it right. So these initiatives are most welcome initiatives. I always feel that we are a little late, but nevertheless, there is never a better time. So better late than never. Right?
So, sir, what is can you explain a little bit more about this Semiconductor Mission 2.0? Because 1.0 created the background, and then it also developed the manpower required for it. Now is the time to push this boundary beyond.
Well, the first mission was all about establishing fab, the hardware. The second mission is all about IP creation, doing the kind of work which is required to support these fabs in the future, and have your own IP rather than, you take, let's say, designs from elsewhere and manufacture them here. That will also happen. That will also continue. But in the current situation where so much is riding on who owns these chips or the intellectual properties in them, is so critical for not just for a strategic sector anymore. It's also for consumers.
Yes.
Right?
Yes.
There is so much about security of these chips or whatever you are using, I'm using, all of us are using as electronics. What goes in there? How secured is it? And how do you know that it is secure? And we have plenty of proof that there is all kinds of possibility of espionage and data theft and whatnot. So it becomes incredibly critical for a country to have your own designs, your own IP, particularly for a country like India. We are a subcontinent,
Right.
a huge nation. From consumer point of view or from any point of view you look at, uh, you know, world can be led by only countries like India. It's becoming more and more clear, and so we have to have sovereignty, if you will, in your silicon, and that's what these missions are about.
Okay. And so India is joining the supply chain. Where do you see its contribution will be mostly, dominant? I would say that important in that particular line, because we also lack in the raw materials and all that.
Even raw materials can be developed. It's not any magic. As China has, shown the whole world that if you plan properly and if you plan long term, you can actually own very, very critical parts of supply chain so that nobody can hold you hostage. That's what in the current geopolitics that's emerging as the basic thing,
Right, right.
that you can't be held hostage, just because somebody wishes to,
Right.
right? And supply chain disruptions that happen, there are two aspects to it. Supply chain disruption that happens because of some natural calamity. Something happens and you have supply chain disruption, and can you reconfigure supply chains? That's a classical problem, in operations research, and we understand that. But there are deliberate supply chain disruptions, and those tend to be more strategic. So there, having your own supply chain, including critical materials, and including certain leverage, that if I'm dependent on you for something, you must be dependent on me for something.
Right.
Otherwise, the relationship doesn't work.
Yes.
Right? You are vulnerable. And I think that's what we must address.
Right. So, there if you see the technology which is going beyond the current stages, like a 2 nanometer kind of logic, and there is also a lot of buzz that India whether should go towards that or towards the wide band semiconductor. So, what is your views that what should be the balancing act? And
all those nodes which are 2 nanometers or 1.5 now in production, those nodes are extremely expensive. And we know that. It's not just only expense, it's the kind of infrastructure it needs and kind of expertise it needs. All of that, plays a critical role there. But, there is plenty of stuff to be done at higher nodes. So, I do not see why one has to fret about or obsess about these, extremely, lower scale nodes. Yes, those are used in, the current processes that really, really matter for, AI and AI chips.
right.
But, there is so much that you can do with, as you pointed out, wideband semiconductors or, higher gallium nitride, power, RF, all of these. And even in silicon, most of automotive electronics is still at much higher nodes. So, if you look at the market and how much can you sell or how much can you produce, export, and use in your own market, there is so much volume for higher nodes, right?
Yes.
So there is, I don't think that there is a criticality in getting into 2 nanometer.
Right.
There are players in that area, and that's good. I would focus on
Wide band.
yes.
Yeah. Yes,
Certainly.
your work also,
Yes.
some of the work are in that area. Would you like to speak a little bit about that?
No, it's more to do with what we see as critical needs of India, right? As a community, as I said, that look, EV is a big market.
Yes.
What EV demands is high power electronics. High power electronics you can do beautifully with gallium nitride, silicon carbide. These are the materials that we can use easily. Even RF, all antennas, radars, right? So there is a whole lot of market or applications that you could address possibly with these materials. Huge market, and it's not just for India, right? You can export this worldwide. There aren't many players in these areas,
right?
So that's why I think focusing on these areas is important, and that's why we are doing it. And as you know, at Center for Nanoscience and Engineering at IIC, IITH Semiconductors is totally focused on this, and they're doing very well.
Yeah, since you mentioned about sense, you would like to, in short, a story, like how you started and where it has reached, and do you think in addition to meet challenges of the current electronics, that SANS or similar such centers should come up elsewhere strategically?
Yeah, so that story, as you know, you were part of that story. It's pretty old now, right? Started thinking about it.
It's still relevant.
Very, very relevant. Actually, more relevant today than it was ever.
Yes.
There, it was in our head. It was very relevant because we wanted India to participate in this sphere, and there was no way to do that without starting things like that. In 2002, while you were there, this realization one day I had in a classroom, coming out of the classroom, that we graduate about 2 lakh electronics engineers in this country every year, and not a single student touches silicon during their 4 years of electronics education. And that realization just froze me, that what are we doing with our young people? How are you ever going to have technology coming out of this country where, a transistor is mere diagram in the heads of all your students? They have never even seen what it might look like, what's the physical look and feel for it. And that's when, I talked to Naukant Bhatt, and I said, Naukant, we have to change this narrative for the whole country. We must do this. We must have a place for our young to get in, to get their hands dirty, so to speak. You get your hands dirty in a clean room, in this in this business, and experiment and understand, this technology. So it was not just, nanoelectronics on one hand, which is what Naukant was focusing on, and MEMS that I was focusing on, and we could think of marrying the two in this facility, and then many of our other colleagues joined. Vasu with materials expertise, Anil with physics, and so that's how we began SENSE. And the dream was that we want to change the narrative of what nanoelectronics or electronics education is like in India for the coming generations.
Right.
So it wasn't about just our own research or for IISc. And once we built the center, which took us a good 10 years, to build, and a lot of hard work. If any corporate folks say that they work harder than, folks in the academia, I can give them a run for their money. We did not know when it was day, when it was night, the kind of effort we put, and that's the kind of effort you need for things like that. Doing it first time.
In fact, we have also seen such few meetings that had...
Right, yeah. That's why I said that you were witness to that. how intense those things were. But if you want to do things that change generations, okay, and bring completely new paradigms in higher education for a whole society, for a whole country, it's a very different obsession, and you have to get you have to get obsessed to do that,
Right.
which is what we did. But what it has done for the country is so good to see. What it has
Right.
done after that, IIT Bombay and IIC, we came together and we built these centers, and after that now there are at least 8 other centers, right? Far more students getting educated with hands-on experience. They know what technology is. They can work in fabs. They can design new devices completely. They can make them, fabricate them, assemble them, test them, package them. That expertise which was completely absent. Completely absent.
Right.
And today 800 institutions using our facility at IIC Science. Fantastic.
Remarkable, and congratulations.
Thank you.
Yeah. So while, sir, you were talking about when you were coming out of the class, you realized that unless the students see the silicon, he can't really think of design. Similarly, when you talk about the semiconductor technology, which is being on demand in the current stage, so what kind of education do you think the students should undergo to also, because things are moving from chips to chiplets?
Yeah, it's the kind of expertise you need requires a broader education. It's not. See, VLSI design has been around in this country for a long time, and our students have done very well. There are so many fabulous companies in the country, right? They have been around for a long time. Bangalore alone probably has 300, 400 such companies. So it's not just that. That's an old story. Now, you see, the chips are becoming more and more custom made for all kinds of applications, particularly with edge computing taking off and AI coming in. Now the complexity of design is more, and how do you package them along with sensors, along with it's not just logic and memory anymore. There are various kinds of devices which need to be packaged. So packaging is becoming very, very complex.
Right.
So packaging is another area, right? Thermal management is a nightmare nowadays. So that is one area where you need to train students.
Okay.
In fabrication, what fabrication means, right? It's all about processes, process engineering, right? So can you have engineers trained in processes where they understand nuances of everything involved in the process, right? You have done so much fabrication yourself, and you know that processes on one hand are like recipes for cooking,
Right.
where you have so many ingredients and so many things to control, temperature, pressure, flow. All of this is very, very nuanced. So when you are trying to do process experimentation, you need solid knowledge of chemistry, which mostly, engineers don't do, right?
Right.
Physics. Solid knowledge of physics and chemistry is what gives you a handle on materials,
I see.
and materials is the key to all fabrication, right?
Okay.
So I think that process training for coming up with new processes, once a process is established, it's locked in.
Right.
It's completely automated and you can't do anything. But if you want to come up with new things, you need new processes. You want to use alternate materials. You have to come up with, or you have to design new processes for these new materials to be incorporated in this workflow. So that is another area where I don't think we have focused training, right?
Right.
So in this whole business of design, fabrication, testing, packaging and testing, you have at each step, you have training requirements. I don't think that we have the entire chain set up.
Okay. So, sir, you talked about fabrication process, and now we see that the process like lithography has also varied. For example, people talk about extreme UV lithography and then electrolithography. So, can you tell the difference and which one is, let us say, can be useful for Indian consent?
You see, these are two very disparate things. Extreme UV, which is right now what is used for production, and that's a completely bulk process, right? So flood exposure, and you get a whole wafer done in one go. That's not yet possible with electrolithography. Electrolithography is still a serial process.
Okay.
So, till we figure out how electrolithography can be done at much faster speed and with multiple probes, so that you can compete. Well, I mean, even in terms of resolution, it doesn't compete yet.
Right.
It's not
Right.
there yet. Yeah, you can get, with some acrobatics, we can get to maybe 20 nanometers or 50 nanometers, but it is still far away. Electrolithography needs far more development to become a process which can be used reliably the way, photolithography is used with extreme UV.
Right.
So I think that the mainstay is still going to remain with extreme UV. However, we have to think about developing newer processes. This is already hit the limit now. Where do we go from here? How do we do it?
Okay.
Is still on the table.
Right. And you see that there are a lot of companies, private companies, who started establishing fab in India. Earlier, when we used to talk about SCL or Siri, and then in Bangalore, Sitar, and of course, few labs now in Bangalore has become a hub of silicon. So, how do you see, which one do you think that will really change the game in this particular area for India?
You mean private?
Yes, yes.
Of
Because
course.
one is, I would say, towards in Gujarat, another one is in northeast, in Assam. Generally,
Yeah,
they are
but
putting up.
it's different kinds of fabs. Tatas. You are referring to
Yes,
Tatas.
yes.
Yeah. Now,
Even in Bangalore, I think Apple fabrication facilities have come.
Foxconn. Yeah, but
Yes.
those are all assembly
Okay.
and testing. These are all assembly and testing, except for Tata's fab in Dholera, which is the actual chip fabrication.
I see.
All the others are, testing and packaging and assembly. Yeah.
Okay. So, right now you were mentioning that the key for the complete development would be the packaging. And this is where we have to, for example, if you also take EV, so battery management
Yeah.
was one of the
Yeah.
biggest problem, but
Yeah.
Indian engineers and the companies took it. Even if you see startups
Yeah,
in
yeah.
many institutes,
Yes.
only for the battery thermal management. So, any view that how we should handle such kind of bottleneck in the thermal management for the systems in packaging?
Well, all of these are deep engineering problems, right? There is no shortcut.
Right.
What we were not doing previously was taking these challenges to actually manufacture these things here, right? And pay attention to R&D that was required for developing your products.
Right.
It's not magic and it's not rocket science either, right? You just need to be at it. So now that capital is available, previously it's not like we didn't have talent in this country. But now capital is available,
Right.
which means new companies can come up.
Mhm.
If new companies come up, and hey, you have a country full of young people.
Yes.
Young people have a lot of energy and also, they have brains, right?
And they take challenges also.
Correct. It's just provide them right kind of training.
Yes.
And we are we are ready to jump at any product you tell me. I think we can build. We can build in this country. We have the talent that can be utilized for such things. When I say that, yes, that kind of training is perhaps lacking, training demand comes when something exists, right? That,
Yes.
okay, we need this.
Yes.
Otherwise,
Yes.
you're just doing training for what? For fun,
Right.
So, now that these companies are coming up, that kind of training can be provided. As I said, there is enough wisdom, there is enough experience, and experience from folks who have worked all over the world. That experience is also there in India. Is good academics and young people. What else do you need?
Right.
Just focus on products and we can do it.
Right.
So it's not just battery. Any product you tell me, we can do it.
Yes, good to know, and also you're I would say that you are very hopeful as well as confident about the future India.
And it's not hope, as in just dreaming. Been there, done that,
Yeah.
right?
Yes.
When nothing existed, we made things exist.
Right.
We built products,
Yes.
we made products, commercialized them, from scratch. So we know the path that you have to take.
Right.
So I'm not talking in air. I'm talking, what we have experienced and what I have seen.
Right. Right. So while developing this product, tell us the biggest bottleneck where you really had to spend more time. I would say in whatever aspect you would like to explain.
Even today, we have real bottlenecks, and our bottlenecks are supply chain bottlenecks. It is still a serious challenge. You need something specific for making a product. You go looking for it, and you find that, okay, there is no supplier in India. There is some supplier in Switzerland or Netherlands or somewhere. Just searching for that and getting that right is a nightmare. So, and also when machines go down, all these semiconductor processing machines, right? Fab process tools. These tools are all coming from outside. I'm so happy that now there are some companies in India that are taking initiative to start building semiconductor tools. So that, if some tool goes down, then you are at the mercy of whenever they can come and repair it. So this kind of problem we face so many times. Delays happened so many times that what we should have been able to do in 5 years took us 14 years to do.
Yeah, right. So you are suggesting that two things, the future people should look for is to identify the supply chain centers.
Absolutely.
And second one is to develop service centers.
Right.
Sort of for the equipment.
That's right.
Because one equipment cost.
Right, so much. And we as a country can do this very well. We have people with a lot of talent. Once you let them loose, after some equipment, they are able to figure out everything, right? How to repair it, how to get it serviced, how to, make it work. Of course, the tools are also becoming more sophisticated, and it's all in electronics now, and that's a much bigger problem, right? Because if everything is on the motherboard, and if something goes wrong, then the only thing you can do is replace the motherboard. But fortunately, in this technology, there are lots of areas, vacuum systems, for example, a very, very key area, right, in all of this business of silicon fabrication. Vacuum technology, so you can certainly have lots of people who can fix these systems, right? And it's one of the key areas. Controls, right?
Yes.
Temperature control. So these areas are easy, where we could have our own supply chain, starting from the components that you need for them to servicing them.
Right.
You remember Hind High Vac, right?
Yes,
As a
yes.
company, it started a long time ago. A faculty member from Indian Institute of Science started it, and it still is the company that rules
Yeah.
in the country.
Right.
Over what, last 40 years, 50 years. I mean, there should have been 10 Hind High Vacs by now.
Yeah.
So yes, we do need to address these issues,
Yeah.
supply chain ones, for accelerating our work.
So, sir, during our discussion, PhD, we talked a lot about damping, damping of cantilevers. How do you think energy dissipation still rules the overall design of sensors in this era?
So in MEMS, right? You're talking about MEMS or NEMS. Any system where you are trying to get signals out of its motion, any vibration, right? And if you're trying to get signals from there, then you have to pay attention to how much energy is going where. It's all about these energy exchanges, because the signals are so small, so tiny, right? In that tiny signal, if there is dissipation, then what you get is almost useless, right? Because you can't really measure it above the noise floor. So that's why I think understanding energy dissipation at that scale becomes very, very critical, just from the point of view of what you designed it for, how it will operate, what part of energy is under your control, for actuation,
Right.
what part of energy gets transferred in the sensing mode, right? These are things that you actually compute, you design for. Now, if somebody comes and steals some of that energy that you haven't accounted for, then your design goes for a toss, right? And that's what dissipation does. And at that scale, we have had so little experience of what role different things play, and that's why understanding dissipation became so critical.
Okay. So now you see that earlier we were talking about dissipation for the sensors in the ambient.
Yes,
People now talk about deep space, deep sea.
right.
So the variability will, of course, becoming
Huge.
huge.
Right.
So it becomes even more important, right?
Of course, absolutely. We worked on intrinsic losses, right?
Yes.
So even if you are in space, you can't get rid of intrinsic losses,
Yeah.
right? So those losses become much more pronounced, because that's the only one that is there now.
Right.
And intrinsic losses is something that we just lump together and say, okay, this one we can ascribe to. But now we need to understand intrinsic losses much better.
Mm.
Where is this energy? It's not just thermoelastic damping, right? What happens to phonon interaction, photons, where do they interact? What kind of losses happen because of that? There's a whole bit of work that you need to do to understand clearly where energy is getting lost, right, in space. Of course, underwater it's a totally different matter. But of course, these devices are packaged devices.
Right.
And also in space with temperature, right? Temperatures can go down so much, right? At that temperature, what happens to these losses?
Thermal noise.
Yes. Well, thermal noise will go down, but
Yeah.
then, you still need to
Have a signal.
Yes, yes. And you need to know that at that temperature, whatever models we use for computing our losses,
Right.
those models will break down.
Sir, can you talk something about your work in CMUT and its significance in deep sea
Well,
applications?
CMUTs, we started with CMUTs, but now we have been working mostly on PMUTs, piezoelectric, micro machine ultrasound transducers. When I started working on CMUTs long time ago, that was 2003, 4, something like that. We had trouble getting circuits for conversion from charge or from capacitance to voltage, right? CMOS are capacitive, as you know. So the kind of signals that we were getting from CMOS, or we wanted from CMOS, it was becoming really hard to get that above noise floor. At that point, autofarad circuitry wasn't available. So that's why I pivoted to PMUTs. And also it looked like for PMUTs, somehow the electronics was simpler. We didn't have to do too much of acrobatics. So PMUTs we have developed. Now PMUTs are, these are transducers that, can transmit ultrasound waves of low frequencies as well as a very high frequency. You can go anywhere from 20 kilohertz to 10, 20 megahertz, and even there are papers, there are people who work in gigahertz. Unbelievable. So now these kinds of devices for exploration in the deep sea, or underwater. Underwater, the signals travel much longer, right? Dissipation isn't that high for sound waves. So you can use this for exploring, for imaging, for finding things under sea much better than with anything else. Obviously, deep sea, there is no light there. Right? So these waves become far more interesting for exploring those areas.
Okay.
And that's why these developments are useful.
So people say that in sea, the communication is one thing which is lacking. Like in open or space, you have communication or the signaling is quite understood and standard. But still, under sea, they are talking about large distance communication. How?
No, but sonars, sonars have been developed for this purpose for a long time, right?
Yeah.
It's not new. You can obviously, all technologies that we have come up with, they become better and better and better with time. So now the need for exploration requires a different kind of communication. It's not just, that there is, underwater submarine and that wants to communicate with, some other ship or somebody. It's not just about that. You want to develop, let's say, underwater weapons. I wouldn't like that, but, let's say you want to do that. That will have to have on it, these kinds of transmitters that you can still communicate with. So it's important, and also now we are trying to understand more and more about underwater life. Even for coral reefs, for example, understanding their health is so important, preserving them is so important for ecology, for environment. So there, how do we image those really from close proximity, autonomously, and also not stock photography that, you are there. You should be able to zoom in and see where interesting things are autonomously. So you could mount these on radars, on robots, underwater robots, and you could do this, right? So if you have really, really good systems for communication and for imaging, right? Both. Um, you will be able to do deep sea exploration far more than we have done ever, which is a frontier today.
Right. I remember my son was talking about Fish 365 long back when he was small. And I said, what is this? And he said, don't steal my idea. The future autonomous fish coming up. Yeah, so from sea to let's go to space. And notably your work, I would say one of the many work that got really used in Indian space. So first of all, many congratulations.
Thank you.
And how was the feeling, and what was, some story about that?
Yeah, so getting our gyro on ISRO mission was really a really goosebumps moment for me. It was the day it was launched. I was just holding my breath. That we had worked very hard, and
Right.
J.P. Reddy, who is now scientist with ISRO, he was PhD student with me, and he had worked so hard on developing a MEMS gyro in India, right? See, this is the thing that people don't realize about technology. It's not that we didn't know how gyros work, right? But to make it work in silicon and fabricate the whole thing in India took us so long, because those recipes that you use for fabrication, you try that, you think that it will work.
Right.
It doesn't. So many runs we had to do
Right.
to get it right. And then, once you get it right, then of course that's still on the wafer. You have to dice it, you have to take it out, you have to still package it, you have to still put a lot of electronics. All credit to ISRO that they held our hand at every step.
I see.
Okay, they knew that if the sensor has to be built, it's only Sense that can do it. It's only we could do it, right? So they were very supportive in making that happen. But the rest of the processes, where they had to build the required electronics for it and do the packaging, they did all of that.
Okay.
And that's how this partnership worked so well for us, that it became a clear success. And it was really gratifying, very satisfying. That look, this work. Once you do it, then you know that now we will be able to develop all kinds of gyros that ISRO requires, or our strategic sector requires, defense requires. We can develop those. No big deal. But you need to get that first product out to get that confidence.
Right.
Every time you feel like you're so close, and something goes wrong, right?
Yeah.
Something goes wrong. That's how these things are.
Right.
So yes, it has been a remarkable journey. Without fabrication, we started working on gyros probably 25 years ago or so. Yeah, in 2000, some master's thesis. But those were mostly to play with designs and see if we understand design well enough. The real work started, fabrication started only after Sense came into existence in 2012.
Right. So many congratulations, sir. And it is also a proud moment of our lab, as well as the Indian national. I think many people, I hear a lot of good story about how the facilities and facilitation for using Sense have been set up. That's really a role model for many of us to really follow. Now coming from your Chandrayaan and your current work, where you are also focusing in tissues, cells, and some human senses. So we are thinking of going to space in the spacecraft. So how do you think the human integrated sensor, how long it will?
There is still ways to go. the integration of sensors in humans. there is a lot of time required for that. It's because once you, if it is not a wearable, right? If you want to implant any sensors in humans, then the regulatory things are just way too complicated, and also rightly so, right? Because it's a question of human life. I think a more pertinent question perhaps is that how close can we get to how human body, or that for that matter natural systems, have evolved sensors, right? How close can we get to those sensors? I think the work on sensors, and as you mentioned, with cells, etc. This is the work that we are doing with ultrasound sensors to study mechanobiology of cells, and how you can selectively, kill cells, those cells, cancerous cells, and how you can also stimulate certain cells which have become dormant and are not doing what they should be doing, right? So cell stimulation is a field which can be used for therapeutics very, very effectively. We are studying that. But you are also aware of the work we did with crickets, where we tried to understand.
Yes, acoustics.
Right. We tried to understand how crickets produce such high intensity, loud noise, right, with in such small volume. That work opened up a whole area, as far as I'm concerned, to understand nature's way of designing sensors or actuators.
Okay.
Nature's design and how it uses scaling, what design principles it uses. That's, see, when we talk about biomimicry, usually we talk about just copying the function. How something is, a bird flaps its wings and it can fly. So can you design a wing which flaps and it can fly? So you are trying to copy the function. But the design that nature uses is very, very clever design. Right? So understanding the design principles that nature has used and the scaling rules it uses for scaling the same design to various length scales. That's a very, very potent area of research, and that excites me a lot. I wish I had time to do that. Today, as you know, I'm more involved in trying to give directions to a university, right? Set up things.
Since you talked about this, so let us go from your work in science to the administration.
Sure.
So first of all, congratulations for taking up this very interesting university, and if you can talk a little bit about it, that how it started and why did you take that decision to move from ISC to that place, and now it is more than 5 years.
Yeah, it's 5 years.
How do you see its growth and establishing it as a unique university?
So I see Plaksha as initiation of a new revolution in education space in India. You do need very, very bold initiatives to change how education has been in this country. Engineering education itself is, its basic structure is fairly old. The engineering education as it exists today, in most schools in the world, is post-World War II construct of how engineering needed to be done. And that's what we have used all these decades, just little short of a century, right? But 21st century is very, very different, different from what we have seen up to 20th century. the information democratization and now even compute democratization is unbelievable.
Right.
You know?
Right.
Given that information is readily available everywhere, your old construct of what education was for, it's certainly not for giving out information anymore, right? We can't compete with what exists.
Yes.
So then, education got to change drastically.
Right.
And then there are all these new techniques and tools, like I call, AI, machine learning, all of this as new calculus.
Yes.
It's as foundational today
Right.
as calculus was for us to understand, the world models, right? So, lock, stock and barrel changes were required. And there wasn't anything on the horizon I saw which was giving you that freedom to do.
Right.
So when Plaksha University came and, I chatted with the founders and they had the dream and aspiration of doing precisely that. And they said that we'll give you a clean slate. You can rewrite the playbook of engineering. I mean, that kind of opportunity comes once in several lifetimes, I suppose, a few lifetimes. So that's why I took that up, because I did not like the way we were doing engineering education in our country. And I wanted to do my bit to change that. If you think that, oh, you have this hotshot idea, well, come and show, right? It's no good just talking about it.
Yes.
So, it's a big challenge. It's a huge challenge, right? But I always prefer that to just sitting somewhere and talking and, just cribbing about how bad things are. This is what happened with sense. That's why sense happened. And that's why this university is happening. So, you want to do something, you think you have good ideas, there are some other people who also think that it's a good idea.
Right.
Hey, do it. Right. And that's why I took up the challenge.
Excellent. So, we hear a lot of good things about your university, and we'll have some time opportunity to also come and visit.
Please do.
Now, since you are on the hot seat of the university, so many faculties, young faculties, raring to publish paper and produce product. So now, when you see that everything is available, right? Even in publishing, writing papers, all your calculator like AI tools are doing it. So, how do you see where we should go towards the skill and technology development, or it's like a writing and publishing kind of?
So this publish or perish, right, paradigm that existed in academia is really, really outdated. I would say that those days are not far off that it will be publish and perish. If publish, so you perish. And why I'm saying that is that the way research enterprise has changed. Now, universities are required to do translational research, which companies used to do.
Right.
They're required to do translational research far more. Also, because the way technology has changed, very small teams can build products, which was not possible before.
Right.
You needed a big company to be able to make any product. Now you can, almost like a single person's enterprise can exist today, right? Even building hardware products. I'm not talking about doing some app and software. No. So, because of this radical change, universities are more and more getting into training students to build products. Take your research ideas from the lab and create an IP and build that. Now, you obviously want to build a successful product, which means you want to protect your IP. IP is protected by two ways. One is you have a patent. The other one is you don't tell anybody what you do in the product, right? It remains your secret sauce, right? So that secret sauce now will become more and more in demand, which means you can't publish it. If you are building products which are really niche products and you want it to be in the market with your distinction, then you will have to hide the secrets of it. Whereas universities prided themselves in bringing out knowledge to society. That, hey, look what we have discovered, here it is. Today you discover something and first thing you want to do is protect that idea so that nobody else steals it, right?
That's true.
So it's a very different world. And now publishing, with all these tools, there are some 25,000 papers coming per week. Who is going to read these papers?
Right. That's true.
So I think this is going to change drastically.
Okay.
And faculty members are going to be working more and more towards translational research. That doesn't mean that the need for doing fundamental science will go away.
Yeah,
you will still need that.
Yes.
But my guess is that the fundamental science will find its way to other groups who are your friends.
Interdisciplinary kind of.
Well, interdisciplinary, but I'm talking about, you will talk to your friend that, hey, look what I have discovered, let's make a product out of it. And you will not like to publish it. So this is very, very likely scenario.
So more collaboration with entrepreneurship, humanities and all will come up.
That of course, that has to happen because, products require that. Products can't be built by a,
So, sir, you would like, you will be happy to know, IITH has also put technology development, IP, also as a part for PhD graduation and all. So, a lot of 350 plus startups have generated around 1500 crores of.
Congratulations.
So, a lot of,
Wonderful.
Towards that idea we are doing. So, this problem will also come up while you recruit faculty.
Yes.
So, do you, again, what you will see in future? I'm not talking about.
My mantra for recruiting both faculty and students has always been the same. I look for fire in the belly. Is this person really, really motivated? Rest of things can be taught.
Right.
Motivation is intrinsic. I mean, even motivation you can get from other folks, right? But there is something called intrinsic motivation.
Right.
Are you the kind of a person who is really curious? You want to do things, you want to change, you're restless, right? Those people tend to take up significant challenges and work on them.
Right.
So, after that, what do you do? In what form you throw the challenge at them and in what form it comes out is up to you. Whether you want a paper which shakes up the whole world or whether you want a product that really becomes useful for humanity. Right. The origin of that is not very different. Of course, people are differently skilled. There will be somebody who is very good at coming up with new ideas, but not with the execution of the idea, right?
Right.
So not every faculty member will start building products. There will be faculty members who will be very, very deep in figuring out new things, new knowledge, generating new knowledge. And great, we need that. Right. And there will be other faculty members who will run with an idea and then build a product out of it that even the original person who came up with the idea, right, wouldn't be able to recognize that, wow, I didn't think that you could do this with this idea, right?
Right.
We need those people.
Sir, you have worked a lot in nonlinear right from your PhD in Cornell and then in MEMS.
Yes.
Now you are seat in administration.
Yes.
Where do you see the weak and strong nonlinearity?
Oh man. University administration is far, far more non-linear than any of the things that we know. It's just different complexity altogether, right? It's because so many human beings are involved, so many processes are involved, and all human beings are non-linear, right? So,
Yeah.
so when you have so many coupled systems
Right.
with weak and strong coupling all over the place, and then you throw in government in there for regulation, right? And then the whole market, which is students and parents, it's an incredible mix, very non-linear. University administration.
So with this, sir, we are concluding all, but still we have little rapid fire kind of question.
Go ahead.
Yeah. So where your heart lies, where you feel like a student in ISC or Plaksha, or both.
जिगर के दो टुकड़े.
That's a good answer. And the best time to have a breakthrough, whether 2 a.m. in the lab or 7 a.m. over coffee. Or I would add one, evening with your favorite drinks.
I would say 2 a.m. in the lab for breakthrough always is the kind of, that's when you get this peace to work on things. Yeah.
One word to describe your PhD guiding style or faculty mentoring.
Give them freedom.
What you would enjoy the most? Mathematical modeling in nonlinear systems or experiments in multi subsystems?
Both. Experiments and modeling. If you don't bring the two of them, you will never get the truth. One is not alone enough.
Okay. Coming to the semiconductor, what do you like the most, silicon or gallium nitride?
I still like silicon.
What is the biggest myth about Indian fab? Is it the water or motivation or lack of talent?
Lack of planning and vision.
Okay. Whether Moore's law is dead or it is on some life support.
Moore's law, as we knew it, is dead, but it has a new avatar in terms of functional scaling.
I see. So what is your favorite process, or I would be a little personal, the characterization?
Well, that's the thing that I knew the best. So certainly characterization.
The first Indian-made consumer chip, when do you predict?
Next year, 27.
27?
Yes.
Oh, nice. What is the future of education? It is degree or skills?
None of the two.
Mhm.
Education is the future of education. Real education. Real education is not just
Overall.
skills. Yes. It's not just skills or it's degree. It's learning how to be intellectually curious, hungry throughout your life.
So, who is the greatest teacher? Is a failure in the clean room or a textbook by Feynman?
Oh, by far the failure in the clean room. No comparison. Failure meaning failure anywhere in experiments.
Yes. So, AI in the classroom is a ultimate co-pilot or it's a distraction?
Bit of both.
Mhm.
A lot of judicious choice is required here. It does both.
So, one thing that a student at IITH or any higher education should know or should learn to align with the current requirement of the industry or
I think nothing beats just being intellectually hungry and curious.
Right. So, retirement for a researcher, does it really exist, or you change your frequency?
Retirement for a researcher doesn't exist. Retirement is not, research is not a profession. It's a way of living life.
Can you tell one word about Chandrayaan?
Pride of the nation, aspiration of the nation.
What is more stressful, your PhD viva or countdown of the satellite of Chandrayaan?
Oh, certainly a countdown of Chandrayaan. That was far more stressful.
And the next frontier for man, deep sea, deep space.
Both.
And your favorite material, you told silicon, but among that, silicon or polysilicon?
Silicon. Silicon, okay. Far more versatile.
Yeah, with this, sir, we conclude, and it is a great pleasure to have you. And always wait. I remember the first day when I met you, I was really liked your way of the guiding student, talking students, and still your MATLAB is quite famous. So thank you for mentoring us. It's a great pleasure to have you here.
My pleasure, Ashok. Thank you for inviting me. It's always good to talk to you, and always great to get connected. Thank you.
Thank you so much. And we will come again with another series of podcasts with experts like sir. Thanks a lot.